254 in week 3. Any question before we proceed? Let me talk a little bit about the quiz. Inshallah, what we will do is I was thinking of making a mock test in order to see how you can upload files. I want you to write your solutions and then upload them to Blackboard. The only thing is, from experience, Blackboard, file submissions in Blackboard have big problems. The biggest of which are sometimes you don't know whether you uploaded the right file or not. Okay. I decided to do the following. I'll give you the questions. I'll give you the questions on the test on Blackboard. But when it comes to the submission, once the time finishes, I will let you, scan and save your files as preferably as PDF, and then I will open a link which will be an assignment. Okay, it's not part of the test. So you will go there and you know how to upload assignments. صح ولا لا? You can upload it, and you'll basically have 5 or 6 minutes, to upload it, then download it and make sure that you uploaded the right file. مش كده أحسن؟
I think it's better.
Yeah.
إن شاء الله نجرب.
إن شاء الله. And I will send an announcement in this regard, and please, try to be familiar of how you take pictures, and you can use Office Lens. You can use. I heard CamScan is another option, but in my experience, Office Lens is good. If you do it as a document or even black and white document, it is very clear. You can put it, export it as a PDF file. So it's good. Anyways, I'll mention this regarding the protocol of the online exam. It's the same as the protocol that was done by all those freshman courses. Where you have you log on to MS Teams on your mobile, and you log on to Blackboard on the laptop, and you have your mic on. You need to show the screen. You need to show the space in front of you, since this is a closed book, closed notes, closed everything exam file. Inshallah, I will upload this and post it on our Blackboard. Okay. Right. This is one thing. The other thing is, I would like to apologize for my delay in uploading the notes, and the reason for that is, for some reason, either the university has put some restrictions, or maybe Microsoft itself has put some restrictions, but for some reason, Dropbox was not syncing with my PowerPoint. When I opened the PowerPoint, it used to do that very nicely, in the last couple of weeks. But day before yesterday, starting from this week, it seems that there was a big problem. I moved on. Now I'm using the OneDrive, and it seems in the OneDrive is okay. I already posted the notes, the previous notes until day before yesterday, now are also posted. You can check that. I really apologize for that, but inshallah, يعني from now on خلص بطلنا عن الدروب بوكس. I'll just use the OneDrive, you know, for our notes. ماشي يا شباب؟ طيب. So any questions before we proceed? Let me try to share my screen here.
In the quiz, are there going to be a need for a calculator? Will there be a big number calculations that will take time, or?
No, but if there are calculations, you need to carry them without without a calculator. Try to be familiar of doing things without a calculator. No calculators are allowed. You reminded me. I need to add this to the. I need to add this to the protocol. طيب. Let me see now. Okay. Okay. So this is where we are, huh? So now what we will do is we will look at an interesting part of or an interesting form of prime numbers, which are called Mersenne primes, Now, as we have seen in the previous theorem, we have shown that there are infinitely many primes, right? We have shown that there are infinitely many primes. Therefore, you know, if you give me any positive integer, I can find an integer greater than that integer. If you give me any positive integer, I can find an integer that is greater than that integer. Okay? Now, there is an ongoing quest to discover larger and larger prime numbers. And as I think mentioned this before, large prime numbers are crucial nowadays for, based on the current computing power that we have, are crucial for certain encryption techniques, public encryption techniques. And I know that, things are, improving very quickly as far as efficiency of execution is concerned, to try to, break those encryptions and, decipher them quicker. So prime numbers, to know, big prime numbers is actually very important for these techniques, right? طيب. However, it might not, finding the largest such prime number might not be used necessarily in those techniques, but it's basically for the love of, science, for the love of the knowledge. People might be interested in pursuing large numbers. So for almost all the last 300 years, the largest prime known has been an integer of the special form 2 to the power p minus 1, where p is also prime. Okay? For the last 300 years, the prime numbers, the largest prime numbers that we know of are of this form, 2 to the power p minus 1. Okay? Where p is prime. Now, any prime number in this form is basically called a Mersenne prime. Okay? It's basically called a Mersenne prime. Right. Now, let me ask you the following question based on what I have said and based on what you see on the slide. Is it true that if p is a prime number, then I can conclude that 2 to the power p minus 1 is a prime?
Can you repeat the question, please?
I'll repeat the question. if P is a prime number, can I conclude that 2 to the power P minus 1 is a prime number?
Yes, I think.
Yes. طب anybody says no? Anybody says no? Or thinks no? MashaAllah, all of
Yes,
you. Yes,
I
you
think
say
no.
no, صح?
Yeah,
Why not?
because for example, 2 to the power 4 is 16.
2 to the
16
power.
minus 1 is 15. 15 is not a prime.
Hey, but 4 is 4 a prime?
Wait, what?
Is 4 a prime number? Until you said 2 to the power 4 minus 1, صح?
Oh, so P has to be prime.
Yes.
Oh, so
يا شباب. Based on what you see on the slide, the
I think
answer
no.
is most likely yes or no. No. هات لنشوف ليش.
2 to power 7 minus 1 تطلع 255.
طيب.
وهذا
لحظة
مش
شوي. You're absolutely wrong.
why?
2 to the power 7.
7 is 128.
128.
2 to the power 7 is 128.
Oh, yeah. I see.
يا شباب. And for me, it is very obvious from the slide that the answer is no.
Because it's the largest prime number. He never mentioned that the small numbers are also have the same rule.
I did not mention. Okay, so maybe this is one hint, but there is even a bigger hint. There is even a bigger hint. Look at this. It says here that the largest prime known has been an integer of the special form 2 to the power p minus 1, صح? طيب, assume that I found an integer of this form 2 to the power p minus 1.
It's not necessarily a prime.
No, I told you I already found a prime number of the form 2 to the power p minus 1. So now 2 to the power p minus 1 is a prime, صح?
Okay.
Right. If I want a bigger number, just raise it raise 2 to this power and then subtract 1. And if this is also prime, since we know that this is also prime, معناته keep doing this 2 to that power minus 1. So there is no meaning for searching for large prime numbers, صح ولا لا؟ خلاص, once you have 2 to the power p minus 1 is a prime, خلاص, keep, recursively, keep raised to the power 2, subtract 1. What you get, raised to the power 2, subtract 1. صح? But that's not the case. That is not the case. Okay? Now, so now the question is, that might come in somebody's mind is, well, how come the largest numbers are of this form 2 to the power p minus 1? Why not from other forms? Okay, and the reason that the largest known prime has usually been a Mersenne prime is that there is an extremely efficient test known as the Lucas-Slamer test for determining whether 2 to the power p minus 1 is prime or not. Okay, now I don't know actually what is that test or how does that test work, but if you are interested, you can just Google Mersenne primes. There is a whole society and web page, GMPS, I think, where people around the world who are interested in finding the largest known Mersenne prime basically have that what you call what's happening. Okay. Right. Okay. So on that page you might see the test. Even they might share the code. You can maybe get the code and keep your PC busy for a couple of I don't know, weeks or so, testing numbers, whether they are prime or not. Okay. Right. Okay, let me go back to the slide then. So, okay. So basically, the largest number that has been reported in your textbook was 2 to the power 43,112,609 minus 1. Okay, and this was in early 2011. This was in early 2011. Now, the largest found so far is 2 to the power 82,589,933 minus 1. And this was found or documented on December 21st, 2018. The guy who found it, I think, was on December 7th, and it seems the official announcement came on December 21st. This prime number, by the way, has 24,862,048 digits. It has this number of digits. Okay, so that's the largest. That's the largest so far. In the previous set of slides that you might have seen, I need to switch my phone off so that this doesn't happen again. Let me just put it on. Okay, I'll just put it on airplane mode. Okay. Fine. Okay. So distribution of prime numbers. Let's look at the prime number theorem, and then I need somebody to explain it to us. Okay, I'm going to read it now, and then I need somebody to explain. The prime number theorem says the following: the ratio of the number of primes not exceeding pi and not exceeding x, which is denoted by pi x. So pi x is the number of primes not exceeding x, is denoted by pi x. The ratio of the number of primes not exceeding x, which is called pi x, and x divided by the natural logarithm of x, or x divided by ln x, approaches 1 as x grows without bound. Approaches 1 as x grows without bound. Read this for 1 minute, and then I need somebody to explain. Okay, يلا يا شباب. Any explanation? Is anybody يا شباب, can you turn on your mic, your cameras? أنا زي كان عم بحكي مع حالي صراحة.
No, doctor, but we are figuring it out. يعني it's not a straightforward answer or you are thinking.
طيب.
As far as I can see, it
أيوة.
says here that no matter what, the ratio of the number of primes will never exceed like 1.
No, that's not what it says. It's a good attempt, yeah, Abbad, but you really missed it.
I
You
see.
really missed it. Look at the table. Have a sneak peek at the table, and see whether you can rephrase this theorem. يلا يا شباب.
دكتور,
نعم.
I see x pi of x and x over ln of x is over and over is getting the same.
أيوة. This is what the prime number theorem says. It basically says that if x, grows without bound, the number of prime numbers that are less than or equal to x is approximately equal to x over ln x. Is approximately equal to x over ln x. And this is obvious, for example, here in the table. If you look at the table, we have like 10 to the power 3, 1000. How many prime numbers less than or equal to 1000? Well, there are 168. Okay. And what is the value of 1000 divided by ln 1000? Well, it is 144.8. And if you look at the ratio, it is 1.161. Okay, it is 1.161. So it is off by approximately 16%, صح? It is off by approximately 16%. Right. When you go to 1 million, the number of prime numbers less than 1 million is 78,498. Then, and 1 million divided by ln 1 million is 72,382.4. Now, the ratio is 1.084. It is off by 8.4% only. It is off by 8.4%. If you go down to 10 to the power 10, if you look at 10 to the power 10, look at these two numbers, 455 million. X over ln x is 434 million plus, right? And look at, it is off by how much? 4.8%. Now, so the more the number grows, the number of prime numbers that are less than, that number becomes very close to, x over ln x. Becomes very close to x over ln x. So this is what the prime number theorem. This is what the prime number theorem says. It's basically giving you that the number of primes is increases in this way, and as you can see, it increases indefinitely. صح؟ يعني how can we sense that the number of prime numbers is infinite? Well, take the limit of x over ln x. What's the limit of x over ln x as x goes to infinity?
Infinity.
Infinity. Use the L'Hopital's rule, صح?
Mm-hmm.
Use L'Hopital's rule. So infinity over infinity. So you can take the derivative of the denominator and the numerator. The derivative of x is 1. The derivative of ln x is 1 over x. صح? So the x will go out up. So now
be
you
x.
have, so it will be x. So the limit of x as s goes to infinity is infinity. Okay, so this is what the distribution of primes. This is what the the prime number theorem gives us, right? It gives us a sense of how many primes do you have that are less than or equal to x. Right. So every odd integer is one of the two arithmetic progressions, 4k plus 1 or 4k plus 3 for all integer k, for all positive k's, 1, 2, 3, 4, etc. Okay? Every odd integer is one of the two arithmetic progressions. Right. Before I continue, how many arithmetic progressions do I have of the form 4k plus b? Okay, so let's assume, so 4k plus b, and k is greater than or equal to 1, okay, integer. How many different arithmetic progressions like this do we have?
I think it's if k goes from 1 to infinity, it's infinity.
It's much less than infinity. It's finite.
It's finite.
Yes.
Then it's 2, because we have 4k plus 1, 4k plus 3.
Well, we said 4k plus 1 or 4k plus 3 is for odd. But what about the rest?
Mhm.
What about the rest?
Take b to be even, the next two even numbers.
Take b to be the next.
Since 4k plus 1 and 4k plus 3 is for odd numbers.
طيب. طيب ايش رايك ب 4k plus 0
and 4k plus 2
and 4k plus 2? طيب و 4k plus 4 مش هذا هو نفسه 4 times k plus 1؟
Yes.
This basically repeats.
Okay, so this
It's the same. It's the same answer. It's the same question. The answer to this is the same answer to the question. Well, any number.
when you continue the sequence
When you
beyond
divide
4.
it, when you divide it by 4, what are the possible remainders? 0, 1, 2, 3. بس. So we have 4 progressions, right? We have 4k plus 0, 4k plus 1, 4k plus 2, 4k plus 3. We have 4 progressions. 4k plus 4 is the same as 4k plus 0.
2 for even, 2 for odd.
2 for even, 2 for odd. Isn't it obvious that 4k plus 0 or 4k plus 2 are even?
Mm-hmm.
They are even. So 4k plus 1 and 4k plus 3 are odd, right? 4k plus 1 and 4k plus 3 are definitely odd. Right. Let's go back. So we know that every odd integer is in one of these two progressions, right? It cannot be in any other one. It cannot be in any other one. Right. The question is, are there infinitely many primes in both of these arithmetic progressions? Now, why do we ask this question? Because we know that prime numbers that are greater than 2 are all odd numbers. Huh? Are all odd numbers. So do they, are there, infinitely many odd numbers here? Infinitely many prime numbers here, and infinitely many prime numbers here? Okay, well, what about primes of the form, ak plus b, where k, of course, can be any positive integer, and no integer greater than 1 divides both a and b, which means that they are relatively prime. We will see what do we mean by relatively prime towards the end of the lecture. Okay, so when a and b are such that, 1 is the greatest common divisor between a and b, do we have infinitely many prime numbers of this form? And the answer is yes. It was proven by a German mathematician. His name is Dirichlet, or I don't know how to pronounce it, to tell you the truth. But basically, he's the one who proved it. So he proved it for this general form, right? So in particular, there are infinitely many primes of this form, or there are infinitely many primes of this form. Okay? Right. Now, why are we mentioning this? Well, we are mentioning this because now there are some conjectures and open problems about prime numbers. Okay? For example, so before we continue, let's settle first, what do we mean by conjecture? Who can tell us what do we mean by conjecture?
And operator.
ايش؟ Say that again. And oh, that's a conjunction.
Okay.
هلا فهمت عليك. That's a conjunction. That's not a conjecture. That's a
I
conjunction.
think it's a conclusion of a problem, or I would not say solution, but
You're very close. You're very close. So
it's like a strong guess.
أيوة. It's not a fact. It's a proposition that you think is correct, and all the current evidence, all the current examples that you have tried corroborate that it is correct, but you don't have a proof.
So I can say hypothesis.
It's kind of it's a conjecture. يعني there is belief in it is correct, but we have not proved it. Okay, يعني even if you tried it for 10, 100 million numbers, it will not work. It will not be sufficient or enough, to say that it is correct. It has to have a formal proof. It has to have a formal proof. Right. So for example, it would be useful to have a function f of n such that f of n is prime for all positive integers. Such that f of n is prime for all positive integers. It's very nice, just give it n, it will give you a prime number. Give it an n, it will give you a prime number associated with n. For example, look at the polynomial f of n equal n squared minus n plus 41. Now, this polynomial has the interesting property that f of n is prime for all positive integers n not exceeding 40. Not exceeding 40. Okay? Right. Question. This can lead us to the conjecture that f of n is prime for all positive integers n. Can we settle this conjecture? Now, if you don't believe me that it works for all n not exceeding 40, when you go home, try it. F of 1, f of 2, f of 3, f of 4, f of 5, f of 6, f of 7, try it and make sure, that it is true that every number is what you call is a prime number. That every such number is a prime number. So now my question to you is this a conjecture? Or can we prove that it is correct or incorrect? يلا يا شباب صحصحوا شوي.
Conjecture.
conjecture بس do you think it is correct ولا incorrect؟
The f of n above or a general f of n that works with all integers?
Yeah, for all n. If you give it any n, it should give you a prime
Should
number.
give-
See that this is what the conjecture says. This can lead us to the conjecture that f of n is prime for all positive integers n. So f of n اللي هي n square minus n plus 41 is prime for all n. Is this conjecture correct?
No,
No, why not? أيوة يا أسامة.
because not exceeding 40.
أيوة. See, there is a hint in not exceeding 40. See, it says that it is prime for all positive integers and not exceeding. So it worked for 40 numbers. It worked for 40 numbers. طيب. So which one do you think will break this rule?
41.
41. Let's try 41 يا شباب. Let us try 41. What is f of 41? Well, f of 41 is equal to 41 square صح? minus
خلاص بس
41
41 square.
plus 41 صح؟
صح.
طيب وهذا ايش بيساوي؟
41 square.
41 square.
41 square هذا prime؟
Not prime.
Not prime. So we can settle this conjecture by saying, you know, this conjecture is incorrect. And the proof is that I come up with a counterexample. I found an n, which is 41, such that f of 41 is a composite, is not a prime number.
Doctor,
Now,
if we change 41 to be 51.
so change it to 51. And assume that the number that came is prime.
Yeah, but it will be not exceeding 50 maybe.
Not exceeding بس احنا هلا اثبتنا لك انه ال 41 does not work.
Yes.
We have counterexample now.
فكيف بتقول لي not exceeding 50؟ Not exceeding 50 it means انه المفروض كان ال f of 41 gives a prime number صح ولا لا؟
صحيح.
ما f of 41 ما اعطاك prime number. Okay. So f of 41 is not a prime number.
Okay.
طيب. So let's take some, you know, some conjectures that exist so far, and before we, you know, go back to problem solving. Okay, before we go back to problem solving. Now, the Goldbach's conjecture says the following. The original conjecture says the following: that every odd integer n, where n is greater than 5, is the sum of 3 primes. Alaykum salam. Is the sum of 3 prime numbers. Any odd integer greater than 5. Okay? Any odd integer greater than 5. So, for example, 9. 9 is odd, صح? 9 is equal to what? Some three prime numbers.
3 threes.
3 threes. 3 plus 3 plus 3. طيب 15 odd صح؟ What are the 3 prime numbers?
5 plus 5 plus 5.
Why am I choosing easy ones? 5 plus 5 plus 5. طيب how about 19?
Uh, 7 plus 7 plus 5
7
plus 7 plus 5
plus 7 plus 5. Excellent. Okay. Now, this is a conjecture. Nowadays, this conjecture is equivalent, as it was shown by Euler, the great mathematician. It's equivalent to the following conjecture, that every even integer, n, where n is greater than 2, is the sum of two primes. Every even integer, n, where n is greater than 2, is the sum of two primes. Now, this conjecture here was verified by hand for numbers up to millions. By hand. شباب قعدوا they did it by hand up to millions. Okay? And this was verified by computers for even integers up to 1.6 multiplied by 10 to the power 18. 1.6 multiplied by 10 to the power 18. And by the way, this was during the time when I prepared those slides. So maybe now this number is bigger. Okay, I wouldn't be surprised if this number was. I wouldn't be surprised if this number was bigger. Okay, but it is still a conjecture. Nobody was able to prove it. Okay, nobody was able to prove it. Right. Another one. There are infinitely many primes of the form n squared plus 1, where n is a positive integer. Where n is a positive integer. Can anybody give me on the chat, I need to see 3 different such numbers. Yalla. 3 different prime numbers of the form n squared plus 1. Let's see. Three numbers of the form n squared plus 1. طيب نواف قال 2 اللي هو 5 و 17 مصطفى 17 عبارة عن ايش؟ 4 سكوير بلس 1 صح؟ 16 بلس 1 17 و مشعل قال 2 2 اللي هي 1 سكوير بلس 1 كمان صحيح. اوكي 2 اللي هي 1 square plus 1 is also correct. So these are three such examples. Note that this is also still a conjunction. Okay, if you prove any one of these, you will become very famous, very famous. Okay. طيب محمد الهاشم قال لي 4 و6 بس يا محمد لا ال4 برايم ولا ال6 برايم صح ولا لا؟
He said that n is an integer. It's not right.
Hey, n is an
2
integer.
square plus 1.
انت what you said
Square
is
plus 1.
2 square plus 1 و 2 to the power 4 plus 1 وال4 square يا ربي plus 1 وال6 square plus 1 صح؟
Yeah, it
yes,
will
yes.
be
37.
5, 17, 37.
ممتاز. Yeah, this I misunderstood you. Okay, I misunderstood you. طيب أسامة ليش كتبت لي 100 يا أسامة؟ قصدك على 101؟
ايوه غلط قبل 10 أس 10 هي 10 تربيع بلس 1.
اوكي. ال 101 وال 101 is prime.
ايوه
101 is a prime number. طيب. Okay. So this is still a conjecture. However, the best result currently known is the following theorem. There are infinitely many positive integers n such that n squared plus 1 is prime or the product of at most 2 primes. Or the product of at most 2 primes. This is proven. Okay, this is proven. What we are left with is to show that that they are prime only, صح? Without the or part, the product of at most two primes. طيب. Twin prime conjecture. Twin primes are pairs of primes that differ by 2. For example, 3 and 5. Both are prime. The difference is 2. 5 and 7. Difference is 2. 11 and 13. Difference is 2. 17 and 19. The difference is 2. 4,967 and 4,969. The difference is 2. The conjecture says there are infinitely many twin primes. There are infinitely many twin primes. Okay. Right. Let me ask you the following question. Do you think when the numbers grow bigger, the possibility of a number and the number plus 2 to be prime, do you think it will go up or it would go down?
I think it will go down.
It will go down, sir. It will definitely go down. Because we will have much more, composite numbers. Okay. The possibility of composite numbers basically increases, right? Yet, this is still a conjecture. Nobody was able to prove that, twin primes are infinite. Again, what is proven is that there are infinitely many pairs P and P plus 2, where P is a prime and P plus 2 is just like the previous theorem, either a prime or the product of at most 2 primes. Or the product of at most 2 primes. Okay, so these are still, these are still conjunctions. Okay, these are still conjunctions. So let's go back now to problem solving. Okay, let's go back to problem solving. So let's take the definition of greatest common divisor and least common multiple. I think you have seen this in high school. If A and B are integers, not both 0, the largest integer D, such that D divides A and D divides B, is called the greatest common divisor. Okay, it's called the greatest common divisor of A and B. Okay, it's called the greatest common divisor of A and B. So, for example, what is the greatest common divisor of 36 and 28?
Eight or 4.
4. Huh? The greatest common divisor of 36 and 28 is 4. 36 is 4 multiplied by 9. 28 is 4 multiplied by 7. Huh? So 4 is the greatest integer that will divide both A and B. That will divide both 36 and 28. Okay, so we denote this by GCD AB. We denote this by GCD AB. Right. The integers A and B are relatively prime if their greatest common divisor is 1. If their greatest common divisor is 1, we call them relatively prime. Relatively prime. Now, if you choose any 2 prime numbers, are they going to be relatively prime?
If I choose what?
Any 2 prime numbers, are they going to be relatively prime?
No. Yes, they will be.
They will be
Yes.
relatively prime.
Yes.
Huh? If I give you any 2 prime number, 5 and 7, 7 and 11, 11 and I don't know, all of them are relatively prime because
the only common divisor is 1.
Is 1. Type. Can any one of you give me 2 composite numbers that are relatively prime? 2 composite numbers that are relatively prime.
8 and 15.
Excellent. 8 and 15. Somebody on the chat said 4 and 9. Both of them are not primes, but they are relatively prime. Okay, they are relatively prime because their greatest common divisor is 1. Because their greatest common divisor is 1. So now the question is, how can I find the greatest common divisor? Okay, how can I find the greatest common divisor? Well, one way to find the greatest common divisor of two integers is to find all the positive common divisors of both integers. Okay, is to find all positive common divisors of both integers, and then take the largest, and then take the largest. But this is kind of basically doing too much. Okay, it's basically doing too much. For example, let's look at what was the example that I gave, 36 to 28. So for 36 and 28, you will think, what divides 36? Well, 2, 4, 9, 18, right? And then 36. صح? طيب, what about 28? Well, you have 2, you have 4, you have 7, you have 14. صح? Did I miss anything?
I think 6 in this 36.
I missed 6. Oh, I missed 3 and 6. Huh?
Yeah.
I missed 3 and 6. So is it so what is the one that is maximum and in both lists? Well, you can see that 4 is the one. But this is not really a good an efficient way. Huh? This is really not an efficient way. طيب, another way to find the greatest common divisor of two positive integers is to use the prime factorization of these integers. So know basically what are the prime numbers that constitute this number, okay? And then write it in terms of, the prime representation. Using the prime representation. Just like, what we said, any number is either a prime number or a product of primes, صح? Remember, day before yesterday? It's either a prime number or product of primes. So for example, if we go back to the example of 36 and 28, what are the prime factors of 36? Well, they are basically 2 and 3, صح? For 36 is 2 and 3, right? So these are the prime factors of 36. What are the prime factors of 28?
2 and 7.
2 and 7. So basically, what I need to do is I need to write the 28 and the 36. I will need to write the 28 and the 36 as follows. So 28, I need to write it as 2 to some power multiplied by 3 to some power multiplied by 7 to some power. And I need to write 36 as 2 to some power multiplied by 3 to some power multiplied by 7 to some power. So what is 28? 28 is 2 to the power what times 3 to the power what times 7 to the power what?
2 to the power 2.
2 to the power 2.
3 to the power 0.
3 to the power 0.
7 to the power 1.
7 to the power 1. Exactly. 4 multiplied by 7 is 28. طيب, will 36?
2 to the power of 2.
2 to the power of 2.
3 to the power 2.
3 to the power 2.
7 to the power 0.
7 to the power 0. Okay. Right. Okay, so I wrote 28 and 36 in this way. I wrote 28 and 36 in this way. Now, how can I find the greatest common divisor? Well, it says here that the greatest common divisor of A and B is basically P1 to the minimum of P1 to the minimum of A1 and B1 multiplied by P2 to the minimum of A2, B2 multiplied by P3 minimum A3, B3 all the way multiplied by Pn minimum of AN, Bn. So if I want to apply this on 28 and 36, so what is GCD of 28 and 36? So how am I going to write it? Well, it's going to be 2 to the power
2 to the power of minimum of 2 of 2.
minimum of
2.
2 and 2. What is the minimum of 2 and 2?
2.
2 multiplied by 3 to the
3 to
power,
the power minimum of 0 and 2.
which is 0, multiplied by 7 to the power,
Minimum of 0 and 1, which is 0.
which is 0. So this is equal to 4. Okay.
So
Now,
how we get 2 and 3 and 7?
how did we get 2 and 3 and 7?
Yeah.
Well, basically, 2 is because 28 is 2 squared times 7. Well, 36 is 2 squared times 3 squared. So what are the primes in both of them? A 2 with 3 with 7.
Oh, okay. We're taking both of them.
Yes.
Okay.
Yes, because we need to write it in this form. You know,
Mhm.
P1 to the power A1, P2, and the same set of primes here. Okay? Right. So this is called the greatest common divisor. Now, the integers A1, A2 up to AN are called pairwise relatively prime if the greatest common divisor between any two of them is equal to 1. Okay? Where 1 less than or equal to I less than J less than or equal to N. So what does this say? It says if you choose any two different numbers among A1, A2, AN such that the greatest common divisor between them is equal to 1, then these numbers are called pairwise relatively prime. They are called pairwise relatively prime. So for example, if I choose 8, 9, and let's say 35. Are they pairwise relatively prime? What's the greatest common divisor between 8 and 9?
1.
What is
1.
the greatest common divisor between 9 and 35?
Also 1, I think.
Also 1. What's the greatest common divisor between 8 and 35?
So they are pairwise relatively prime.
So they are pairwise
Relatively prime.
relatively prime. Okay, so this is the definition of pairwise relatively prime. طيب, what about 8, 9, 34?
No, they are not I think
Are not. Why?
there is between the 9 and the 34.
9 and 34. ايش اللي بينهم 9 and 34؟ ترى it's very easy يا شباب، بس انتوا شكلكم خلاص بعد الظهر يا اما you are exhausted or you are doing anything but following me.
8 and 34 have 2 and
34.
have
8 and 34 has 2 صح؟
and mhm.
2 divides 8, 2 divides 34. So these are not, you know, pairwise relatively fine. Okay. طيب, the least common multiple. Well, the least common multiple of positive integers a and b is the smallest positive integer that is divisible by both a and b. Is the smallest positive integer that is divisible by both a and b. This is called the least common multiple. Okay, this is called the least common multiple. How can I find the least common multiple? Well, you can use, if you write a and b just like the way we wrote it to find the greatest common divisor, instead of using a minimum of a1, b1, we use a maximum. We use the maximum of a1, b1. This way we get the least common multiple. So for example, if we apply it for L28 with 36, okay? So this is the GCD. Now, what about the LCM? LCM of 28 and 36. Well, this is equal to what?
2 to the power of 2.
2 to the power of 2.
3 to the power of 2.
3 to the power of 2. Maximum of 0 and 2 is 2. أيوة.
0 to the power of 1. 7 to the power of 1, sorry.
7 to the power of 1. Okay, 7 to the power of 1. So this is basically the least common multiple of 28 and 36. So this number is divisible by 28 without any remainder and is divisible by 36 without any remainder. Okay. Right. So I will leave the proof of this theorem as an exercise. It's a very straightforward proof, a direct proof that basically uses the definitions of a least common multiple with greatest common divisor. So if a and b are positive integers, then a multiplied by b is equal to the greatest common divisor of a and b multiplied by the least common multiple of a and b. The greatest common divisor of a and b multiplied by the least common multiple of a and b. Fine. So now the last thing that we will do today is how can we find the greatest common divisor using what we call the Euclidean algorithm. The Euclidean algorithm. Fine. Now, before doing that, let's prove that the Euclidean algorithm. Assume that we want to find the greatest common divisor between a and b. If you remember by the division algorithm, we can find q and r such that a is equal to b times q plus r, صح ولا لا? Using division algorithm, will r is less than b greater than or equal to 0? Will r is less than b greater than or equal to 0? طيب. Now, if I want to find the greatest common divisor between a and b, assume that the greatest common divisor between a and b is d. Okay, is d. Question: does d divide a?
Yes.
Yes, because it's the greatest common divisor between a and b. So d divides a. Does d divide b?
Also, yeah.
Also, yes. D divides a, d divides b.
B.
The question is, does it divide r?
Should not, right?
Why it should not? If c divides a and c divides b, does c divide a minus b?
Yes.
Yes.
Yes. And a minus b is a minus b multiplied by q is r.
a minus b multiplied by q يا شباب is r. فif d divides a or d divides b q, definitely d divides r. Definitely d divides r. Okay, so that's why and what's the relationship between b and r? Well, r is strictly less than b. R is strictly less than b. So the greatest common divisor between a and b is the greatest common divisor between B and R. طيب, what can you continue? How can you continue? Well, just continue the same thing. البي جيبها هنا. البي, you bring the B here. So you will say B is equal to, B2 Q2 plus, R2. And the greatest common divisor between B and B2 is also a greatest common divisor between B2 and R2. And R2 is less than B2. So you keep continuing, just like, this is basically the algorithm. So X is equal to A, Y is equal to B. Find the remainder, X mod Y. Make X equal Y and Y equal the remainder. And continue. Once Y become equal to 0, the previous remainder becomes the greatest common divisor. The previous remainder becomes the greatest common divisor. طيب. So before we do visits, inshallah, we'll do it next week. Let's do these exercises. Let's start with the first exercise, and I want to see, the fastest answer on Blackboard. What is the greatest common divisor and the least common multiple between these two numbers? بسرعة يا شباب. أول شيء الجي سي دي. حدا يكتب لي الجي سي دي على الشات. What's the greatest common divisor between these two numbers? 2 times 3 times 5 times 7 times 11 times 13, or 2 to the power 11 times 3 to the power 9 times 11 times 17 to the power 14. ليش يا نواف 1؟ وليش يا مصطفى 1؟ ماجد قال 11. مشعل قال 11 times 3 times 2. Now we're talking. Now we are talking. So it is 2 times 3 times 11. Right? Because it's the minimum. طيب. Okay, well, least common multiple. For the least common multiple, if you want power, use this for the power. Like مثلا 2 to the power 3, you can write it this way. Okay, on the chat. You can write it this way. يلا يا شباب. What is the least common multiple? Well, it is 17 to the, let's see Muhammad Khalil, what he wrote. So it's 17 to the power 14 times 11 square. No, times 11 times 2 to the power 11 times 3 to the power 9 times 5 times 7. Okay, so you just take the maximum.
Doctor, just to make sure, were you drawing just now or writing? Because I don't.
I haven't, no. Okay. Fine. Okay, so let's use the Euclidean algorithm to find the greatest common divisor between 123 and 277. Okay, so let's do it here. So GCD of 123 and 277. Okay, 277. So how do I do that? Well, let's divide 277 by 123. So obviously it is 2, صح? 2 times 3 is 6, 2 times 2 is 4, 2 times 1 is 2. So we have 1 here, and 7 minus 4 is 3, 31. So basically, 277 is equal to 123 multiplied by 2 plus 31. Okay, طيب. Now next, what do? I have the 123, the greatest common divisor between 277 and 123 is the same as the greatest common divisor between 123 and 31. So I will say 123 is equal to 31 multiplied by what plus what? Well, let's go to the margin. 123 divided by 31. If we divide 4, 4 will not work, so we will have 3. So this is 3. 3 times 3 is 9. 0. 12 minus 9 is 3. So this is 31 multiplied by 3 plus ايش?
30.
Plus 30. Okay. Now 30 and 31. So 31 is equal to 30 multiplied by what plus what? يلا.
1 plus 1.
1 plus 1. Okay. 1 plus 1. So now we are left with 30 and 1. So 30 is equal to 30 multiplied by أيوة
1 plus 0.
plus 0. So what is the greatest common divisor between them? So GCD of 123 and 277 is equal to 1. Okay, is equal to 1. واضح الطريقة يا شباب؟ طيب, since we have time, let me come up with something which is not that trivial, like so let's see here. Find the GCD of 143 and 221 using the Euclidean algorithm. Now, I would have broken you up to rooms, but you will not see this slide. فمعلش يلا يا شباب. Go ahead. If you have an iPad or a Samsung Tab or whatever idea pad, you can go ahead and do it and share it with us on the screen. Or you can write it, on a piece of paper. Do it on a piece of paper, and then upload it and share it with us. Let's look at it together. Okay, يا شباب, يلا. Let's see who's gonna do it first and fast. Okay. If whoever finishes, raise his hand, huh? Finishes يعني ترى finishes يعني he is ready to share his screen. Okay. If anyone is ready to share his screen, go ahead. يلا يا شباب, if you want to leave as early as possible, you need to answer as early as possible. يا شباب. We're gonna sit here forever then.
I think I've got an answer.
طيب, can you share your screen with us?
I've solved it on a paper.
طيب, مش قلنا لكم take an image save it share it on the screen with us. يلا قبل ما حدا تاني يسويها. whoever يا شباب أول واحد راح يرفع إيده يكون جاهز. I'll ask him to share his screen. معكم يا شباب السكشن الثاني no time finished. لا تورطونا معهم. ايوه يا اسامه يلا جو اهيد.
أنا حليت.
يلا شير.
الشير موجود؟
الشير هيو it's coming في السكه زي ما بيقولوا.
إيه.
until now nothing.
طيب اصبر اني اسوي.
it worked.
او للستيم شو اسمه التيمز نفسه.
إيه. طيب
اوكي الحين الشاشة كاملة صح؟
تمام. Okay, so let's see now. Do you see يا شباب? So he said 221 is equal to 143 multiplied by 1 plus 78. صح? And then, so now we want 143 and 78. So 143 is equal to 78 multiplied by 1 plus 65. Okay? And so again, this is easy. يعني كلهم أرقام يعني they are very close to each other. So 78 and 65. So 78 is equal to 65 multiplied by 1 plus 13. صح? And finally, now we have 65 and 13. Lo and behold, 65 is equal to 13 multiplied by 5 plus 0. 13 multiplied by 5 plus 0. So 5 times 3 is 15, 5 and 1, 5. So, right? So basically, what is the greatest common divisor? Well, it's
15.
The previously, the previous remainder, which is the 13. So inshallah, what we will do next week, we will see how can we write the greatest common divisor between two numbers as a linear combination of the two numbers. As the linear combination of the two numbers. This is inshallah what we will do next week. I'm done, and if you have any question, otherwise I'll close this and open the office hour room, and inshallah we will see you tomorrow night in the quiz. Okay, Shabab?
Okay, thank you.
Okay,
thank you very much. Thank you very much.
الله يعطيك العافية.
الله يعافيكم. نراكم على خير إن شاء الله. سبحانك اللهم وبحمدك أشهد أن لا إله إلا أنت أستغفرك وأتوب إليك.